Right now, KIC 8,462,852 is still dimming, and astronomers at Yale, Caltech, and NASA have no way to stop it. It drops without warning. It recovers without explanation. And every time it does, the best minds on Earth are left staring at their data with nothing. But here's what nobody is telling you: the dimming isn't the strangest part. What's causing it might be. KIC 8,462,852. It doesn't have a famous name yet, but it has a famous mystery. This star sits roughly 1,500 light-years away in the constellation Cygnus. It's an F-type star, slightly bigger than our Sun, slightly hotter, and to every telescope pointed at it, completely ordinary. Until it isn't. NASA's Kepler Space Telescope watched it for 4 years, cataloging the faint flickers of distant suns. Most stars dim predictably. A planet crosses in front, blocks a tiny fraction of light, and you get a clean, repeatable dip. Astronomers call it a transit. They've found thousands of planets this way. So when the Kepler team pulled up KIC 8,462,852, they expected the same thing. What they got instead stopped them cold. This star was doing something that no planet, no natural process, no model they had could explain. The light from KIC 8,462,852 dropped by 22%. 22. A planet, even a massive gas giant like Jupiter, blocks maybe 1% of a star's light. 1%. The largest object you could realistically put in front of a star produces a dip you barely notice. KIC 8,462,852 dropped by 22%. And not once. It dipped again and again in irregular patterns with no predictable timing, no consistent depth, no symmetrical shape. Normal transits look like a clean U. The light dips, holds, then rises back in a mirror image of the descent. These dips were jagged, asymmetric. Some were narrow spikes. Some dragged out for weeks. Some clustered in groups like something enormous or many enormous things were crossing in front of the star all at once. And when astronomers went back through a century of photographic records, they found something that made everything worse. The star had been slowly, steadily fading for over 100 years, so they reached for the obvious explanations. A swarm of comets, maybe thousands of them, orbiting in tight formation, blocking the light in passing. But the math doesn't hold. You'd need an almost impossibly large number of comets perfectly arranged to produce dips that size. And comets don't last a century. Interstellar dust clouds. They'd leave a different spectral fingerprint, an internal stellar process, some kind of unusual variability. No known stellar type behaves this way. One by one, every natural explanation crumbled. Tabitha Bayagian, the astronomer who first flagged this star, whose name it now informally carries, called it the most bizarre star she had ever seen. The team at Yale ran through their checklist and came back with the same answer. Nothing fits. Here is the part they are afraid to say out loud. One explanation was put forward, not by a fringe theorist, not by someone outside the field, but by astronomer Jason Wright at Penn State. He proposed that the dimming pattern was consistent with what you would expect to see if a star were surrounded by a Dyson swarm. Not a Dyson sphere, not the clean shell of science fiction, but a massive network of megastructures, solar collectors, orbital platforms. Things built by a civilization so advanced they were harvesting energy directly from their star. The math works. The irregular dips, the asymmetric shapes, the long-term fading as structures accumulate and block progressively more light, it all fits the model. Astronomers were very careful about how they said this publicly. They called it the least likely explanation. They emphasized natural causes should always come first, but they published it. They let it sit in the literature. And in 2017, a crowd-funded observation campaign watched KIC 8,462,852 dim again in real time. This time they studied the wavelengths of light being blocked. Different wavelengths dimmed at different rates. That matters. Solid, opaque objects, rocks, ice, anything natural block all wavelengths equally. What was blocking this star's light was semi-transparent. It was selective. The implication of that is one scientists have been very slow to voice. But here's the strange part. It shouldn't be possible at all. If the blocking material is semi-transparent, it rules out most solid natural objects. It narrows the field in a direction nobody is comfortable with, and the long-term dimming makes it worse. Between 1890 and 1989, KIC 8,462,852 lost nearly 20% of its total brightness. Across 100 years, nothing in stellar physics produces that kind of sustained, gradual loss without leaving traces we'd recognize: pulsation signatures, chemical markers, infrared excess from heated dust. This star has none of those. It is fading, and it is fading cleanly. Every alternative collapses. Every new observation tightens the constraint. And somewhere in Cygnus right now, 1,500 light-years away, the star is still out there, still dimming. Still doing exactly what it was doing the day we found it. We don't know if it will stop. We don't know what comes next in the dimming curve. And we don't know with any certainty anyone is willing to publish what is actually in front of that star. So tell us, what do you think is blocking the light from KIC 8,462,852? Leave it below, because the astronomers certainly aren't giving us an answer.